So welcome to this recording of lecture 21 of a course in symbolic computation where we compute with functions. So in symbolic computation we compute with symbols and we make expressions. So in this lecture we will define functions that compute expressions. Expressions now no longer in x, y, z, but in any number of variables. We can also define polynomials in several variables as they are defined by lists of coefficients and lists of exponent tuples. So that's the first part. So in the slides I will explain the main concepts and then we go illustrate these concepts with Sage instructions. The second way, or the second important construction how to build functions, is by function composition. So we make more complicated expressions out of simple expressions. So when we think of a polynomial, we think of sums of terms, we think of monomials. So we can build things up. Function composition allows us, it's very useful for modeling, so that will be our third exercise. And the lecture will end with an illustration of Newton's method to compute a sequence of rational approximations where in each step we double the accuracy of the approximation. This fits within the context of functions. One can view the Newton operator as a function that produces functions, or in general that produces expressions. Okay, so let's start with our first exercise. So make expressions as defined by this formula. So this mathematical formula defines a sequence of expressions. So the dimension is n. N is the number of variables, so no longer x, y, z, but x1, x2 up to xn, where the n is also the number of expressions that we are going to make. So in looking at the recipe, perhaps it might be first interesting to focus on the first and the last term. So this is xi to the power 3 minus 1. And also look at an example. So whenever one sees the big sigma or one sees the dot, 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 think of a particular case so you can fill in the dots. It's good also to eventually write that even down and build up the complexity. So there is a sum for indexed by the letter j, where j runs from 1 to n, excluding the diagonal, so excluding the ith element. So here in the example I left out the diagonal element, so there is a gap each time, where, for example, look for I equals 1, where we start at j equals 2. So the j, so one can first ignore the complexity of the coefficient. You see here the j running from 2 to 4, here from 1 to 4, excluding the j equals 2, j equals I. Then the coefficient is j, but then plus I plus 1. So here you see the I is 1. In the first expression, there is the increment of I plus 1 for every coefficient. So increment is thus 2. So 4 and 2, 5 and 3, 6 and 4. And that gap, that increment, increases as the I increases. So that will be our first exercise. So I will structure this lecture in 4 exercises. The second type of exercise is a generalization. So the first exercise is one specific class of polynomials. Here we look at the definition of a random polynomials. So we've seen that SageMath has built-in random generators of polynomials. Here we can define random polynomials ourselves if we structure the data. So looking at a polynomial in several variables, again the n is the number of variables. The other important dimension now is the number of terms. So that's the m. So we have m terms, that means m monomials, m exponent tuples, and m coefficients. So 2 lists define the data for here a polynomial in n variables. And this can be written very compactly mathematically, where we have the big sigma and we have the big pi, which represents the product. So in Python we have encountered the sum, but there is also the prod operator for making products. We can see these 2 operators as operators on lists that reduce the lists essentially to one single object, and that's the expression. So introducing composition, so we can make more complicated expressions from simpler expressions. If we know how to make a monomial, we will know how to make a sum of it. And in some sense that's also the composition principle in the third exercise. So assume that we're interested in modeling a trajectory. So we have a projectile that is launched at time 0, and at time equals 45 it hits the ground again, farther from us, at a distance of 120 miles. So that's the entire exercise. Come up with a simple model. The trajectory, the simplest model is that of a parabola. So we have, and the point of this model is that it separates the geometry, the parabola, from the time. So we first focus on the fact that we have 2 points, a beginning and an end point. We have 2 roots of a quadratic expression. So that defines the quadratic, the parabola, uniquely. So here it is given in this factored form, and here you see the plot. You see this also now defines the altitude, also the top of the parabola. It's nicely symmetric. When you plug in x equals 60, you come up with the height. So whether that is realistic or not, this is a mathematical exercise, but one can tune these parameters. Well, actually there's one parameter, the 120, but one can also see this question differently. If one defines the maximum altitude, then with the shape, with the constraint of the parabola, that will also then define how far the projectile gets. Okay, so that's the geometry. Then as far as the speed, it's a simple model. So we assume constant horizontal speed, and that defines then the formula for the inner function. So at time equals 0, we have 0, so you should see this as a rational number, 120 over 45 multiplied by time t. So at time equals 0, we have 0. At time equals 45, we must have 120. So that's why we have this ratio 120 over 45. Thus then, the model that tells us the altitude of the projectile at any time is given by y after x. So this is written as this function composition. Okay, as our last example or last exercise for today, consider the Newton operator. One step in Newton's method is defined by subtracting from the current approximation x a correction term which is defined by the function value over its derivative. So one can see this n of f as again a function that defines on another function f and on a number x, represented by the symbol x. So running this Newton's method will, when one starts sufficiently close to an actual root, so we are solving now an equation. So starting sufficiently close to a solution, Newton's method will converge quadratically. So we will illustrate this with an application of the finding increasingly more accurate approximations for the square root of 2. So if we start at 2, an integer exact number, then the symbolic computing system will produce rational numbers. And these rational numbers will double in accuracy in each step. So that makes a nice connection with the beginning of the course, where we considered rational approximations. And you could have wondered, why does this go so fast? Well, here is one very fast algorithm to do this. Okay, so we have 4 problems to consider. Let me indicate how to solve these 4 problems using SageMath in a Jupyter kernel. So I will start out with a new Jupyter notebook, starting out by saying that in this lecture 21 we compute expressions with functions. Okay, so there is already a prepared Jupyter notebook, which I will post on the course website. But it's very important that when you do symbolic computation, that you actually do it. Okay, so making expressions with functions. So what is our task? So define f of I for I from 1 to n in n variables. So we will first actually start by making a list of variables. And what is our expression? So our expression fi starts with x underscore I, and then we have the big sum So to emphasize the big sum, I will put brackets around it, big brackets around it, and then I have the j going from 1 but excluding the I. So this is this array notation here. So in the meantime, I hope you will also learn some LaTeX. So we have the subscript of the sum, then the superscript. Oops, that was unfortunate. So I did something really wrong. So from I from 1 to n in n variables, x1, x2, and now you can see that it's probably not good practice to do too much typing before saving or executing. My keyboard was not collaborating with me, so but no problem. So let me continue this. So let me take my own advice and do the expression step by step. So, and perhaps let's do this step by step. So this is a simpler exercise. Let's start with picking one variable. So this is the big N. Perhaps I will do this really the big N. So this is a big value for the little n. It's n equals 4. So as I experiment with this, so I'm going to have a capital X as well. I'm going to make a list of variables. So I want x1, x2, x3, x4, but actually you can't do this. Well, you can do this, but it will not be completely general. So I want to use the capital N as a value, but I want to add, so this is Python, I want to define the names of the variables with a parameter k. So here you see my 4 variables, but defined in a very general expression. So the capital N is 4. Note that the range stops, so the range starts at 0. So I want to start at 1, and it stops at the last index minus 1. Observe that the x naught will give me x1, so be careful of that as well. And then there is the formatting here. I make a string that is parameterized by the decimal representation of the integer k. So this is the percent operator, which formats the internal binary representation for the integer k into the decimal format. So we see 1, 2, 3, 4. Okay, now let me continue. I'm going now to make my expression using the lambda. Again, Python. Why must I use lambda and not the function notation that we did in an earlier lecture? Because that's to prevent evaluation. So we have the index I, which is the parameter, and the other parameter is x. Here I can write little x. So I do xi to the power 3 minus 1. Okay, so this is a first important, I should have documented this probably already a little bit more. So we must use lambda to prevent evaluation. So functions in SageMath are expressions. So when we would define this as a function with a SageMath expression, it would try to evaluate the indexing here. The Python does not do this. So let me illustrate this for one. So here, oops, I must provide the capital X. So here you see the evaluation of the function. And notice that I already made one mistake. I expected to see x1 to the power 3, but I see x2 to the power 3. So the mistake I made was forgetting that the indexing starts at 0. So I have to subtract 1 from this. Okay, so this allows me to define a whole sequence. Perhaps I will use k. Notice the difference between the actual parameters and the formal letters. So we have the big X, which is the list of the variables that is here that replaces the formal parameter little x in the definition of f. Similarly, I use the k here to make that distinction. So k is a local variable within the list comprehension. It replaces the little I in the definition of f. Okay, so let me go back to the original exercise. So we have defined a sequence of expressions, but I wanted to do something a little more complicated, but I got I messed up the latex, so let me try to do that again now. So I have the J that runs so I have my subscript, which is this array, and then I have the superscript, which is the dimension. So J starts at 1, and we are excluding the ith term. Okay, so let's see if that is valid. It is. But I have defined the sigma, but didn't define the I plus j plus 1 times xj. So here we have the general expression that I wanted to make. Okay, quite convenient. I have the general expression here now correctly defined, and I also have the beginning of my f. So here we have the f that I'm going to extend with the sum of the coefficient I plus j plus 1 times xj, but it will be again xj minus 1 because the indexing starts from 0. So I have the sum that I want to make for j in the range 1 to the length of n. Note, it could be natural to say that I need n, but n is the length of x. Okay, so some errors here. So there are too many brackets open and closed, I'm assuming. So I have the sum There we go. And here you see the expression where the length of n should have been the length of n, the length of x plus 1. Okay, so you see me making all these mistakes. So I have the indexing correct, so let me also execute this now for 3. So you see that the gap is growing, so the gap is between the indexing, the index of the xj and the coefficient. So the gap is now 3, and it should be I plus 1. So that I probably made a mistake there as well. But I have not skipped the ijth term, so let me subtract it. So I have the minus I plus 2 times xj minus 1. So that will skip the term and make the gap. So let me do this. So the term that I'm skipping is the ith term. Okay, so it works for I equals 1. Let me see if I have it correct for all i's. Nope, so you see there is still an error here. So the first one is correct, but here I have the term that also should take into account the it is 2 times I plus 1. And here we go. Okay, so that was our first exercise, and that took me quite a while. So important here is the preventing of the evaluation. So the other important thing that you probably have seen as you have seen me stumbling through this, instead of doing the entire expression at once, work piecewise. So first focus on the terms that are simplest. Okay, so this is a specific polynomial system with a very structured, highly structured. Let's look at polynomials in several variables. So making polynomials in any number of variables. So Sage has a built-in random element for this, but let us make our own random polynomials. So a polynomial in n variables. So again, x1, x2, xn. So n is the first dimension. The second dimension is the number of terms, and that is defined by two lists. So we have the list of m coefficients. So say here rational coefficients. and the list of m exponent tuples. Let me fix again a dimension. So for the example, I will define n and m as, say, 5 and 8. Oops, so this should be a code cell. So then I have my list of variables again, where we use the letter x followed by the decimal representation of the index for the index starting at 1 and ending at n plus 1. Okay, so then I want to make random coefficients to make sure that everybody has the same numbers. I will set the random seed to the date for which this lecture is scheduled. So my coefficients are made out of rationals. And I have m coefficients. So here we see the coefficients, random rational numbers. The exponent vectors are made in a very similar fashion. I want lists of tuples, so there are list comprehensions, there are no tuple comprehensions. So what I will do is I will make a list comprehension, and I will convert the list of exponents, so I will take the absolute value of random integer numbers. So now it's good again. I'm trying to do again too much at the same time. So I have m and n as the parameters. So this is a nested tuple. So I have the exponents, and some of the exponents are actually quite large. If I wanted to have a bound on the exponent, I would use the percent for the modulo operator. I would do modulo some bound, but it's okay here as expressions. Notice the list of tuples. So the outer loop went over the m, the same m, that is 8 for the number of coefficients. The inner range went over the number of variables. And there were many brackets, so the bracket around the list comprehension converts to a tuple. Okay, so let me introduce now the product operator. So we have our two lists, the C and the E, but let me make a monomial out of the first exponent vector. So I will make the product of the variables. So I have the ith variable. Perhaps I can do this a little bit nicer. And I have the exponents. I can probably also do this much nicer. So for x e in x, big X, and big E. Oops, it is not as I expected. So the product runs on a list. Okay, and I probably should have done this by one single index and not by two. So what I want to do is I want to take a tuple out of list of tuples, and I must do the zip. Okay, so this was interesting Python. So I take the list of variables and the first tuple of my exponent vectors, so E naught. Now the little e runs over this list, so you see 1, 1, 1, then 3, 2, and the x runs over all the elements in x. Alternatively, I can define, now that this works, so let me define a helper function. Monomial will take on input an x and an e, and it will codify the product. So the product of the, and perhaps I should work with capital letters. So there are the formal names. Note that the product works on a list. So the monomial worked. So I will test this out. Monomial on x and e naught. Again, so I was distracted a little bit. So the prod is just like the sum. You have to use the square brackets of the list that we are making. The list is a list of tuples. If you do not want to work with this zip, you can work with one single index, indexing the elements in x and in e. Notice the difference between the capital X, which are the formal names of the parameters. The little x and the little e are the local variables in this list comprehension. Okay, I'm almost there, so I can now define my polynomial as the sum, but I will also need lambda. I have my names of the variables, I have my coefficients, and I have my exponents. So I will return the sum of the coefficients times the monomials, where the monomials run over x and e. I will now work with the indexing. So I have ck times monomial, where k runs in the range m. And the m is the length of the coefficient vector. So here you see the random polynomial that I make, and for verification, let me list the coefficients and the exponents. Okay, so this is the end of our second exercise. So using a helper function monomial, I have built a polynomial with three input parameters, the names of the variables in x, the coefficients, the rational coefficient c. Notice that Sage will order these monomials in the highest degree, so the 225 with coefficient minus 35 comes first. So let me point this out. So here we have the largest exponent, that is the next to last monomial, next to last coefficient, but comes first. Okay, the next two exercises, for the next two exercises I have 10 minutes left, and that should work because it's not that complicated anymore. So the function composition exercise started out with the modeling of a trajectory. So we model a trajectory subject to time and geometry specifications. So at time equals 0, the projectile is at altitude 0. So that's the first root of our quadratic polynomial, and at time equals 45, the projectile is 120 miles further. So we have our first function with the two roots, x equals 0 and the x equals 120. The signs are kind of important because we want a parabola that is concave down. So just as a check, so let me plot the trajectory for x going from 0 to 120. The aspect ratio, I will squeeze the parabola a little bit, and let me plot it in red. Okay, aspect ratio is misspelled. So here we have the geometry defined in our first function. Two roots define uniquely a quadratic, which is a parabola. And one can see now that this defines the height, so it's nicely symmetric. At x equals 60, we have the height. So one can see also the form of the definition. So we want a positive height. So x 60, 120 minus 60. So we have 60 times 60 is 3,600. So if you think about the roots, you might have written this as x minus 120. But then you would have had a parabola that is concave up. Naturally as a parabola, but not really natural for the trajectory of a projectile. So then we have the two time constraints. So we have x in function of time. So at 120, for x we must have a 0, and the 0 happens for time equals 45. So at time equal 45, the x will be 120. So that's our second function. And then we have the altitude that is defined as y after x. And to verify, let me plot this f of t for t going from 0 to 45, and I want to see 45 as well. So the aspect ratio needs to be 1 over 200, and let me again plot this in red. And now there are no typos, so here you see the decomposition. So the result of this exercise is that we have one function in time, so x is expressed as a function in time and y is a function in x. The final result is the altitude f of t in function of time for any value within our time window. See 5 minutes to solve this question. In the last 5 minutes I will solve the problem with the rational approximation with the Newton operator. So an operator is a general term to define a function that takes one function and returns another function. So defines one Newton step, or one step with Newton method. So we return x minus f of x divided by the derivative of f at x. I can write this like this. So we have the square function that we will be using. So the square of x is x to the power 2 minus 2. So this is the, we want to compute a root. And let us apply this to the square root. So n at 2. Something went wrong here. So I think I have to cheat a little bit. So it is the Newton step that needs to be defined. So I want it to be too fast. So I have our square root is defined in this way. And that will have to be, no, this is fine. Here we have the point that I want to make, and I'm sorry, I'm in a hurry. So the point that I want to make, I have a function, capital N, that takes on input. So let me write that down in a markdown cell. So we have the function n, which takes on input another function, and which returns the function assigned to our SQRT. So we have a function, we'll call it an operator, so the capital N, which is defined by f and x, and here it's a Python function, but it's executed in the SageMath context, so the derivative is defined. For the little f in the formal parameter, I use SQR, which is the definition of x squared minus 2. And then if I run this, I get a function back. So the RSQRT will now be used to make approximations for the square root of 2. So I will run our SQRT starting at 2, and that gives me 3/2 as an approximation for the square root of 2. I make S3 our square root starting from S2. So this is the next approximation, 17/12, and let me do one more step, and that gives me another rational number. So how accurate is this rational number? Well, I will compute the difference of square root of 2 and S4 and evaluate this with 6 or with 8 digits. So you see I have 6 decimal places correct. Let me do one more step to illustrate the quadratic convergence. I will also compute the difference. So it's the absolute difference. So let's not too picky with the relative error. So has error, and now I will have to evaluate this with sufficient precision. So you see my rational numbers are getting larger, but the error, it went from, and actually the error is negative, so could be better to use absolute values. But the important is that in scientific notation, we have the -6 goes to -12. So if you ever wondered why one can compute so fast the rational approximations of irrational numbers, well, we have a method here, the Newton's method, which only needs to be called a couple of times because of this exponential growth in the accuracy of the Newton's method, the quadratic convergence. Okay, I'm going over time with this because I kind of made too many mistakes at the beginning, but I hope nevertheless that this was an interesting lecture to demonstrate how we can make complicated general expressions with functions.